All right, so we'll finish up section 6.2. And the goal is we're going to try to find the trig functions, not just for the quadrantal angles, the 0, 90, 180, and 270, but for any trig, for any angle that's a multiple of 30 or 45. So what we'll do is we'll start in quadrant 1, how you find the trig functions of 30, 60 degrees, and 45 degrees. In radians, they're on the board respectively, pi over 6, pi over 3, and pi over 4. And then we'll look when we go outside of quadrant 1. Okay, we'll look at multiples. Like instead of 30, we could also do 150, because that's 150 is a multiple of 30. And then we'll also do a little bit of work with trig identities. Not a lot, because trig identities is a topic we're going to spend maybe a couple weeks on. So we're not even really going to get into them that much. Just a very, very basic, quick look at what a trig identity is. Okay, so let's see how we do it. So first angle we're going to work with is a 45-degree angle. So this would be 0, that's 90, and 45 would be right in the middle. Okay, if you want to be able to find the trig functions for 45 degrees, you need to know the coordinates for it. Right, so what I've done is drawn in my terminal side for a 45-degree angle. Draw a line straight down from that point, okay, perpendicular to the x-axis. And what we've done is we just created a triangle. Okay. In this triangle, that's a 45-degree angle from the x-axis to the hypotenuse. And if the 45 is at the base and you have a 90, they all have to add to 180. So the top also has to be a 45. I've drawn the same triangle down below, but a little bit bigger. So if we can find out how long the base is, that's going to be x. How far over do you go? And then the height of the triangle, that's y. So we have to find the length of the base and the height. What kind of triangle is this? Besides being a right triangle, it's also something else. Yeah?
Isosceles?
Yeah, what does that mean?
That two sides are the same length?
Yeah, two sides are the same length. Well, we already know one side in this triangle. We know how long the hypotenuse is. We drew this triangle in a unit circle. So this hypotenuse is also the radius of the circle. So how long is the hypotenuse? Remember, it's in a unit circle, and it's the radius. Okay? Yeah, we just need to know the length of the radius in a unit circle. Yeah? Yeah, it's 1. Okay, your radius is 1. Now, we don't know the base and we don't know the height, but we know that they're what? If you compared them to each other. James, the base and the height of this triangle? It's isosceles. They're the same. The base and the height in this triangle are the same, right? Because it's isosceles. So let's call the bottom side x, because I don't know it. How would I represent the height? The bottom side is x, then the height would be, yeah, x. They have to be the same. It's isosceles. Now, we don't know right triangle trig, so we can't use that to solve for x. But there's another formula we could use from geometry, the right triangle. What formula or theorem could we use to find the length of x? Colby? Yeah, we'll use the Pythagorean Theorem. So square each leg, add them together, and that's equal to the hypotenuse squared. Okay, x squared plus x squared gives me 2x squared. Divide each side by 2. I Again, x squared equals a half, but I don't want x squared, I want x. So, Cody, how would I get x by itself?
Square root both sides.
Yep, square root both sides. And when you take the square root of a fraction, the way you do it, you take the square root of the top and the bottom separate. Well, the top, I can take the square root of 1, that's 1. And the bottom is square root 2. Cole, what's wrong with that as a final answer?
You can't have square roots as well.
Right, you can't have a square root in the bottom. So how about, Kobe, can you tell me what do I multiply top and bottom by here?
Square root of 2.
Yep, my square root of 2, square root of 2. And finally I get x. It's the square root of 2 over 2. That's the length of the base. So that's how far over. And it's also how far up. So now we can write our coordinate for 45 degrees. How far over do I have to go from the origin to that point? Yeah, square root 2 over 2. And then how far up do I have to go? Also square root 2 over 2. Anybody recognize that coordinate? Yeah, it's from the homework last night. I didn't tell you it was the coordinate for a 45-degree angle. You didn't need to know that, but now you do. Okay? So the coordinate always, every time you do a 45-degree angle, is square root 2 over 2, comma, square root 2 over 2. Okay, any questions on that? Okay, let's take a look at the 30, 60, 90 triangle. So before we get into examples, let's figure out what the coordinates are for, we'll do 30 degrees and then we'll do 60. Okay, so here's 0, there's 90, and 30 degrees would be about there, less than half. So I'm going to draw in my hypotenuse. Draw a perpendicular straight down to the x-axis. And this is how you would end up with a 30, 60, 90. That's my 30. And that angle up there, that's my 60. Now, like we had before, we know one of the sides in this triangle. We know the hypotenuse is 1. Why? It's the radius of the circle. And the circle is a radius 1. Could I use the same letter to represent the base and the height in this triangle? What do you think, Augustine? Nope, why not?
Because there are 2 different lengths.
Yeah, they're different lengths, and I know they're different lengths because they're different angles. That's a scalene triangle. So if you're going to try to use the Pythagorean theorem here, you could label one side x and one side y, but that's not going to work. Because now you have 2 variables, x and y, but you only have 1 equation. You can't solve that. So we're going to have to do something else. We're going to have to kind of play a trick with this picture a little bit. Right? We're going to do something with this picture. We're going to add to it in a special way. Anybody have a thought what I can do? This is kind of tricky to figure out. But I want to take what I have here. I'm going to do something with it. And it's going to create a new picture that makes this easier to do. Because I actually know the height of this side. The side across from the 30. But I have to do this trick first to show you why I know that. And it involves kind of, well, see if you can get it. Yeah?
Anything to do with sine.
Nope, nothing to do with a trig function. More of like a trick visually. I'm going to take this picture, we're going to make a copy of it, and we're going to reflect it. Okay? So what I want to do is take this triangle, copy it. I'm going to reflect it like, not that way, the other way. And what do you think I'm going to do with it now? Where could I place it? Would this be a good place to place it? Would that help? Where could I place it that would work well here? Yeah?
The bottom.
On the bottom. Okay, so let's try to put it on the bottom. How long is the hypotenuse in the bottom triangle? Yep, it's 1. It's the same as the top. It's a copy. How about this right-hand side? How long is that?
1.
Yeah. How do you know that it's 1 from here to here?
Because it's an equilateral triangle.
Right. What we did by copying and reflecting it is you created an equilateral triangle. That's a 30. That's a 60. So you have 60, 60, 60. 3 angles are the same. 3 sides are the same. Okay, so that's a trick. Now the real point here, I know the whole length of the right-hand side is 1. So how about the length of just the top part? The top half of that equilateral triangle on the right side. It's a half. Okay, we can prove that these 2 triangles are congruent using geometry. So if you have 2 segments added together that total 1, and they have to be congruent, they each have to be a half. Okay, now you don't need the bottom triangle anymore. So if you want to keep it, that's fine. But all we needed it for was to figure out that that right-hand side was a half. Now, you can call the bottom side x and use the Pythagorean Theorem again to solve for it. We already know y. Y is a half. So x squared plus a half squared equals 1 squared. Okay, Kelsey, what's a half squared? Yep, 1/4 equals 1. Bring the 1/4 to the other side. 1 minus 1/4 is 3/4. And Victoria, how do I get rid of that exponent? Square root both sides. So we get x equals square root 3 divided by 2. So now I know the length of the base. From there to there. I know my height. Now I can write my coordinate for 30 degrees. What's the length of the base? Oh, Priya? Okay, so the distance from the origin to where that perpendicular hits the x-axis is square root 3 over 2. And what's my height? Cole? Half. There's your coordinate for a 30-degree angle all the time. So it's much easier to just memorize that, write it down, put it on your reference sheet for the test, so you have that. Now let's look at a 60. Okay, 60 would be more up here. Draw your triangle. The 30 and the 60-degree angle, they're pretty much the same triangle, except you're taking the triangle, instead of having the long side as the base, you've got the short side as the base. Okay. Any thoughts on how my coordinate would change for a 60 now? It's just basically, yeah, so now your short side is a half, and the long side is square root 3 over 2. Okay? Any questions on that? So now we'll try some examples, and then when we get to one, I'll show you how you could extend it into another quadrant. But if you understand the idea of reflections, that's all that really needs to be done. To say, if I wanted you to do this, 150, it's just a 30-degree angle flipped into quadrant 2. So just think about what would happen to your x and your y if you flip it into quadrant 2, or quadrant 3, or quadrant 4. It's all reflections and symmetry. Right? So some things just become negative and some stay positive. Depends on the quadrant. But we'll look at that when we get to it. Okay. So first thing I want you to do is find the 6 trig functions of 45. Okay. Step 1 is determine your coordinate. Okay. What's our What's our coordinate for 45 degrees? James?
Square root of 2 over 2. Square root of 2.
Yep, that's something really you should memorize. Okay, Casey, what would my sine be? Yep, square root 2 over 2. It's the y value. How about cosine 45? Victoria?
Square root of 2 over 2.
Yep, in this case, not the y value, but
Yes.
it's the x. If you accidentally switched them here, you'd still get it right, but in general, the y and x are usually different. And then my tangent. What's my tangent going to be? This is the problem. You already did this in the homework, so.
1.
Yeah, this is 1. Okay, your cosecant, you're going to flip it. You get 2 over root 2, and then it simplifies to, Darren? Yep, just the square root of 2. Since the sine and cosine are the same, so your secant and cosecant. And now to get your cotangent, flip 1. Okay. Jill, what do you get when you flip 1? 1. Okay. So there's the 6 trig functions for 45 degrees. Any questions on that? Yeah.
Wait, why is cosecant square root of 2?
Because when you flip it, you get 2 over root 2, and then multiply top and bottom by root 2. So you're going to get 2 root 2 divided by 2, and the 2's cancel. Okay, let's look at the 30. So what's tricky a little bit about the 30 and the 60 is you got to remember where the 1/2 goes and where the root 3 over 2 goes. You can't switch them. Okay, if you switch them, then you're doing the 60. So what I do is I just make a sketch. Try to draw it somewhat accurately. So there's my 30. That's 0. That's 90. Draw your triangle. And in this case, I can clearly tell the long side is the base. The long side is my x. Okay. Somebody remind me, what's the long side in the 30, 60, 90 triangle? About Andy? What's the long side? Long leg, I should say.
1.
That's the hypotenuse, so just the long leg.
Square root of 3 over 2.
Yep, and the short leg?
Half.
Half. Right, so I know my long leg is square root 3 over 2. That's my x. My shorter leg, 1/2. That's my height. That's my y. And because 30 degrees is an angle in quadrant 1, it's positive, positive. So you don't have to worry about any negatives with x and y here. Right, and fill in your formula. So sine is going to be the y value. Cosine is the x. And tangent is y divided by x. Okay, when you divide y by x, what's going to cancel out? Yeah, the 2's, because they have the same denominator. So it's 1 divided by square root 3. But we need to fix that. And when I fix it, I get root 3 over 3. Keep 1 over square root 3, though, here. Not as the final answer, but it is going to come in handy to do something else. Okay, my cosecant. Okay, Brianna, what's my cosecant? So that would be 2. And somebody tell me, what's that called again? Not the opposite, but the, when you flip it. Colby? Yeah, the reciprocal. Yep, it's a reciprocal. Somebody give me my reciprocal of root 3 over 2. All nice and cleaned up.
2 square root of 3.
Good. 2 square root 3 over 3. And now the cotangent. You've got 2 choices. You've got 2 things that are equal to each other. Which one should I flip? The one on the left or the one on the right? You flip either one. One of them's less work.
On the left.
Yeah, why should you flip the one on the left?
So you don't have to multiply the top and bottom of the square root of 30.
Exactly. If you flip the one on the right, you're going to throw a square root back in the bottom, and then you're going to fix it all over again. If you just flip the one on the left, you flip it and you're done. Right? So it still comes in handy to save that work. So there's your 6 trig functions for 30. And let's look at pi over 3, which if you weren't sure what that is, your first step would be convert to degrees, and it's 60 degrees. Okay, let's make our sketch. There's my 60. Draw my triangle. Okay, bottom side. Victoria, how long is the bottom side here, the base? Yep, that's your 1/2. Because if you were to label this, here's your 60, there's your 30. The 1/2 is always across from the 30. The smallest angle always goes across from the smallest side. Just like the biggest angle goes across from the biggest side. That's the hypotenuse. And then 60, that's the middle angle. So it's across from the other side that's in the middle. That's your square root 3 over 2. So my coordinate is 1/2, comma, square root 3 over 2. Okay, Augustine, what's my sine here?
Sine
Yep, the sine of pi over 3.
2. Wait, no, 1 over 2.
That's my cosine.
Oh, right.
Cosine is 1/2. Cosine is your x.
It'd be square root of 3 over 2.
That's my y. And what about my tangent? Someone else tell me, what do you get when you divide y by x? Yeah.
Square root of 3.
Yeah, just square root of 3. The 2's are going to cancel, and you're left with square root 3 divided by 1. Now flip them all to get the other 3. So 2 root 3 over 3. Flip 1/2, you get 2. Flip square root 3. And you get square root 3 over 3. These are the same answers we just had in the last problem. They're all switched around a little bit. But if you compare the numbers, sine and cosine switched places. Secant and cosecant switched places. And tangent and cotangent switched places. The reason they switched, look at your coordinate. X and y switched places. Okay, that's why they switched. Any questions on that one? Okay, so that's all for first quadrant. So let's try 135. Okay, so now we're going to extend that a little bit. First thing I want to think about is which triangle this is going to be. Is this going to have something to do with a 30, 60, 90 or a 45, 45, 90? Which one do you think? Darren? Yeah, it has to do with the 45, 45, 90 because 135 is a multiple of 45. It's 45 times 3. And if it has to do with a 45, that means it's halfway between a quadrant, in a quadrant. So 135 is about right there. Draw your triangle. Draw your perpendicular. If you want to put your angle, that's a 45. And so is that. What's the length of each side in a 45, 45, 90? Just the length of it. Well, Cody? Yeah. So I need a number though. Because, yeah, the number that we solved for.
are 2 over 2.
Yep, both of them are square root 2 over 2. Now, when you write your coordinate, just be careful you take into account the direction. You're in quadrant 2. So what's your coordinate for 135 in quadrant 2? You're going left and then up. Oh, Cole?
What?
What's your coordinate for 135?
Negative 1, 1.
So go by the sides, how long these sides are. How long that side is?
Negative square root of 2 over 2.
Yep,
Square root of 2 over 2.
square root 2 over 2. Yep. For a second, let's just look at negative 1, 1. If you went left 1 and then up 1, you'd be somewhere around right there. Okay, you'd end up off your circle. I didn't mention that earlier, but that is what a lot of people guess before I show them what a coordinate is for 45 degrees. They guess 1, 1, but that's actually off the circle. But that's good. So you got it. So my sine, Brianna, what's my sine here?
Square root of 2 over 2.
Okay, my cosine, James?
Negative square root of 2.
And my tangent, yeah.
Negative 1.
Yep, you're dividing y by x, and they're the same except for their signs. So two numbers that are the same except the sign's different, it's a negative 1. If you needed the other three, you just flip your sine to get your cosecant, cosine, flip it to get secant, tangent, flip it to get cotangent. Let's try 7 pi over 6. First thing I would probably do, unless you're comfortable with radians, is change to degrees. For now, forget the 7. Can anybody tell me what's pi over 6? How many degrees would that be, pi over 6? Yeah.
120.
So pi is 180 divided by 6.
Yeah, 30.
30. Now it's 7 times that. So how much is this angle?
110.
It's 210. Which quadrant will I be in for 210? Yep. Yep, I'm going to be in the third quadrant. Here's 180. There's 270. But I'm closer to 180. Okay, that's 210. What kind of triangle is this going to be? The 30, 60, 90? Or 45, 45, 90? Yeah.
26, 90.
Good. It's going to be a 30, 60, 90 because 210 is a multiple of 30, not a 45. Draw your hypotenuse. Draw your perpendicular. And if you want to label your angles, that's your 30. And that's your 60. Okay, the side across from the 30, that's always the short side. Side across from the 60, that's always your long side. So you do have to memorize the short side's a half, long side root 3 over 2. And lastly, I need my coordinate. Okay, Colby, what would my coordinate be for 210?
Negative square root of 3 over 2.
Yep.
And negative a half.
Yep, negative, negative. Perfect. Okay, so my sine, negative a half. My cosine is the x value, negative root 3 over 2. And the tangent. Well, let's start with just the sign of the tangent. Is it positive or negative? Darren? Yep, it's positive because you have a negative divided by a negative. So you're going to have 1 over square root 3. And we've done that one before. What will that simplify to? Good. Square root 3 over 3. Okay, so that's the basic idea of unit circle trig. So I could ask you to find any one of the 6 trig functions for 0, 90, 180, or 270. We did those yesterday. Or the 30, 45, and 60 in quadrants 1, 2, 3, or 4. So there's 16 different angles I could ask you about on the unit circle. Okay, if we can't do it on the unit circle, that's when we use a calculator. Right, so what I want to do is evaluate the 6 trig functions for 42 degrees. Okay, so you know to use your calculator if your angle is not a multiple of 30 or 45. Okay, we've said that a couple times. Let's start with the 3 on the left. Okay, the 3 on the left you have buttons for. Okay, what you have to do once you turn on your calculator is make sure you're in the right mode. There's degrees and radians. So to change the mode, let's go to that. Press mode, where it says radians and degrees. This problem is 42 degrees, so I need to switch it. Okay, put it in degrees. And now you just type it in. So sine of 42 is 0.669. They didn't say where to round. Oh, they did. Said 2. Sorry. 2 decimals. So 0.67. Okay, cosine of 42. Just press cosine 42. Hit enter. 0.74. And last one, tangent 42. 0.90. So now the trick is, how are we going to find those 3? There's no buttons for them on the calculator. Okay, any thought how I can do the cosecant of 42? And if you understand how we did it when we did unit circle trig, what we're going to do here is no different. We're going to find the cosecant the same way. So what would we do to get the cosecant? Yeah?
Wouldn't we just flip the numbers we already have?
You just flip the numbers you already have. Okay. So, or you could do it, you could type in 1 divided by the sine of 42. So basically you're doing 1 over 0.67. I didn't use the 0.67 because that's rounded. If I go back to sine 42, that's exact. So you take the sine and you flip it. That's the cosecant. Okay, take the cosine and flip it. That's your secant, 1.35. And the last one, take your tangent and flip it. That's how you get your cotangent, 1.11. Okay, any question on how you evaluate a trig function on a calculator? Okay, what's different about that problem? Same directions. But what do you have to be careful of here? James? That's in radians. Okay, that's the sine of 10 radians and the cosine of 10 radians. So now I have to switch to radians. Now I can type it in. Negative 0.54. And cosine of 10 radians, negative 0.84. Okay, so the point with that one, just be careful whether your problem is degrees or radians. Okay, so in example 6, okay, we were reminded again of that special relationship between sine and cosecant, cosine and secant, tangent and cotangent. You flip one to get the other. Okay, and there's a special name for these when you do the flipping. It's called a reciprocal. And in trig, these are called reciprocal identities. So just as a reminder, maybe I should put up what an identity is first. So an identity is an equation that is true for all appropriate values of the variable. It's an equation that's always true. So in other words, It works with any angle you can think of. It doesn't just work for certain angles. It works for all of them. Here's an identity from Algebra 1. If I gave that as a problem on a test and I asked someone in Algebra 1 to solve it, they would end up with 4 equals 4 as their final answer. All the variables would cancel out. And that's because this equation is an identity. It's always true. I don't care what you pick for x, you can't make it false. Okay? So we're working with pretty much the same thing. Equations that are always true, except they have trig functions in them. They're not just algebraic. They're trigonometric. Okay? So here's what we call there are 3 really reciprocal identities. The 3 on the right are just repeats of the 3 on the left. If you just interchange what's on the other side in the denominator, you get the one that's on the other side. Okay? So if you flip your sine, you get your cosecant. If you flip your cosine, you get your secant. And if you flip your tangent, you get your cotangent. And then if you flip it again, if you take the cotangent and flip it, you change it back to tangent. If you take your secant and flip it, you change it back to cosine, and so on. Leave a little bit of space below these identities. Okay, we're going to have about 4 or 5 more we're going to add to it. And it's probably easier if you have them all in the same section in your notes. So leave, I'd say a couple inches below that. So I want to look at 2 special trig functions, sine and cosine. Okay, sine and cosine have some special properties that some of the other trig functions don't have. Okay? First of all, when we graph them, they're a very nice function. They're a continuous function, meaning you can sketch it without picking up your pencil. Okay, so here's some special properties of sine and cosine. And what I'll do is I'll graph it so you can see a picture, and then you can write these down at the same time. Here's what sine looks like. It goes forever, left and right. Okay, never stops. So the domain is negative infinity to infinity. In other words, you can plug anything you want in for x. You can take the sine of any angle you can think of. It can be in the millions. It can be negative 2,000. You can take the sine of any angle. But notice the range. It doesn't go up and down forever. And the reason for that connects in with the unit circle. When we talked about the unit circle, what letter represented sine? X or Y? Yeah, Y represents sine. What's the highest Y value that you can ever reach on the unit circle? Augustine? 1. Do you remember what angle that occurs at? It's right there, but what that angle was? 90 degrees, good. At 90 degrees, you hit the highest value that sine will ever go. It hits 1. And then down here, we hit the lowest. It's negative 1. Does anybody remember what's the angle for when you go straight down on the y-axis? Oh, Cody? 270. So when you hit 270 degrees, that's the lowest that sine will ever go. The lowest y value you ever hit. And then from there, you're always either between positive 1 and negative 1. Those are the y values that you're always between. That's why the graph looks the way it does. And cosine looks very similar. In fact, cosine is just a horizontal shift. If you took sine and you bumped it to the left a little bit, and by a little bit I mean 90 degrees, they would be the same. Okay? They're just what we call a phase shift or horizontal shift. Okay, here's another formula. It says that if you take the sine, and let's do it in radians, the sine of any number, say like 0.5, and then you take the sine of 0.5, but you add a multiple of 2 pi to it. That's what 2 pi n means. Multiples of 2 pi. 2 pi, 4 pi, 6 pi, 8 pi. N can be any integer you want. Let's see what happens. Get the same thing. Okay, let's try it again. This time, let's let n be, instead of 1, let it be 2. So I really just added 0.5 plus 4 pi. I get the same thing. Let's let n be 3. Same thing. What am I adding? When I add 2 pi each time, that's the same as adding what?
One rotation.
Yeah, I'm adding 1 rotation. I'm basically taking the sine of coterminal angles. All angles that are coterminal have the same value for sine. So in degrees, you could think of 10 degrees and 370. They would have the same sign because they're coterminal. And that also works for cosine. Angles that are coterminal have the same cosine. That's another way of saying this equation in words. Just add or subtract, and n could be negative as well. You can add or subtract as many revolutions as you want from an angle, and the sine and cosine always stays the same. That's called the periodic property for sine and cosine. We'll talk about it more for tangent and other functions later, but just for sine and cosine for now. Okay, so you already have that in your notes, what an identity is. So the last thing I'm going to do is I'm going to give you all the basic trig identities that we're going to work with in this class. They're not all going to be on the test, but I think in your notes it's easier if you have them all in the same spot rather than having some today, some next week, and then some after Christmas. It's going to be too confusing. So we'll just put them on the same page. Okay, you already have these 6. Okay, those are the reciprocal identities. Okay, the next 2 are called the tangent and cotangent identities, and we've already seen them. We talked about them a little earlier. Remember, sine was y, cosine was x. And then we learned if you take y and divide by x, that's how you find the tangent. This is the same thing we already said with unit circle trig. Sine divided by cosine gives you tangent. Okay, if you have a chance, you can try it on your calculator. Pick an angle, 12 degrees. Take the sine of 12, divide by the cosine of 12, write down the answer you get. Then take the tangent of 12. You're going to get the same thing. And if you flip it, if you do cosine over sine, that gives you cotangent. So you might notice between the reciprocal and tangent and cotangent identities, every single trig function can be written either as sine or cosine somehow. Tangent, sine over cosine. Cotangent, cosine over sine. Sine and cosine, well, those are the 2 basic ones. Cosecant, take the sine and flip it. Secant, take the cosine and flip it. So all 6 trig functions can be written just in terms of sine and cosine. And we'll come back to that in about a minute or 2. Okay, the last group of identities, these are called the Pythagorean identities. These will not be on the test, but I just want you to have them all in the same spot in your notes. So your Pythagorean identities are sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. Now, you might be wondering, well, why did he say sine squared and put the 2 where I did, like in the middle of the function in the argument? If you write sine squared and put it in parentheses, or you write it with the 2 where I put it in between the argument and the function, it means the same thing. It's just a short way of writing what I have in parentheses here. Sine squared. Sine times sine. Okay, and these Pythagorean identities can all be rearranged. Okay, I'll show you what I mean. So right now, the top identity is solved for 1. 1 is by itself on the right-hand side. Well, I could solve this identity for sine squared, or for cosine squared, okay, by doing something like that. I could take sine squared, subtract it, and put it on the other side. Okay, all I'm trying to show you here is sometimes trig identities are moved around and rewritten a little bit. This is not a new identity. It's just rewriting the one we already had, putting something else on the other side. Okay? It's kind of like if you took distance equals rate times time. And you said, well, I'm going to do it this way. Distance divided by rate equals time. Okay, same thing. You're just moving something around a little bit. Okay. So everything from Pythagorean identities at the bottom of what's on the left and the top of what's on the right, that part you don't have to know for the test. But again, it's good to have all your identities in the same spot. Okay, now from here, and then the last slide we're going to do, this will be on the test. So your reciprocal, your tangent, and your cotangent identities, the top two groups. You can use those identities with higher powers. So if you flip sine, you get cosecant. What do you think you're going to get if you flipped sine squared? You wouldn't get cosecant, but you would get, what do you think you'd get? Yeah?
Would you get cosecant squared?
Yeah, you get cosecant squared. What about if you flipped sine cubed? What do you think that would give you? Emily? What do you think you get if you flip sine cubed?
What'd you get?
So if you flip sine, you get cosecant. Flip sine squared, you get cosecant squared. If you flip sine cubed, you get cosecant cubed. Okay. What if you flip sine to the fourth? What would that give me? About Andy? Cosecant to the fourth. Okay? These patterns apply to any power you want. Generally, we never have to do it above a 2. Okay? Okay, we said, let's look at one of the tangent and cotangent identities. We said sine divided by cosine is tangent. What do you think sine squared divided by cosine squared would be? Yeah, it would be tangent squared. Tangent squared. If you did sine cubed divided by cosine cubed, it would be tangent cubed. Okay. So you can use these identities, the reciprocal and the tangent and cotangent, with any power you want. Generally, you're not going to ever have to use it above a 2. All right, so the last thing, I said a couple minutes ago that every identity here can be written with just sines and cosines. Right? So if you have something that looks kind of complicated, like a cosecant times tangent, there's probably a way that it can simplify quite a bit. And the goal, or the trick, is to write using only sines and cosines. So to do that, all you have to do is look at 2 groups of identities, your reciprocal and your tangent and cotangent. Don't worry about the Pythagorean ones. You're not going to use those. Not for this. So I want to rewrite cosecant and tangent just using sines and cosines. And if you can do that, something will cancel out. And you'll be left with a nice answer. Okay, let's start with cosecant. Anybody tell me, how do you write cosecant just using sines and cosines? You might need both, or you might just need one in this case. Yeah?
To get cosecant, you use 1 over sine.
Yep, you flip the sign. Good. How about tangent? Somebody else tell me, how can I write tangent just using sines and cosines? Yep, Cody. Sine over cosine. So basically all you're doing here is substitution. You're changing tangent using one of its identities. In this case, we use this one. You changed cosecant using a reciprocal identity. Now, what happens when you multiply these fractions together? Yeah?
You get the sines crossing or cancel out.
Yep, same thing in the top and bottom. Those cancel.
So you get 1 divided by cosecant.
You get 1 divided by, what's COS? You want to help her out? How do you pronounce that one? Cosine. Yep. 1 divided by cosine. And now, what is that? That's another identity. 1 divided, flipping the cosine gives you the Darren? Gives you the secant. So we took an identity that we took an expression that looked kind of complicated, had 2 trig functions. Somehow we changed it to sine and cosine, so things canceled out, and we ended up with something a lot simpler, with just 1 trig function. Okay, let's try this one. If we have time, we'll try the last one, but that'll be the last one if we do it. How do we rewrite secant? James?
1 over cosine.
Good. 1 over cosine. Now cosine, it already is cosine, so don't change it. If something is cosine, just leave it alone. What I'll do, though, is I'll make it a fraction. What do you get when you multiply those together?
1.
Yeah, you just get 1. So you don't even end up with a trig function. Okay, so your final answer is just a number in this case, just a 1. Okay, and the last one. We're going to write it in terms of sine and cosine. Okay, what's cotangent? How can we write that with sines and cosines? Oh, Casey? Good. So it's cosine over sine. And how about cosecant? How can we write cosecant? Just with sines and cosines. Oh, Colby?
Sine over cosine.
That would be tangent. Cosecant is a reciprocal, so it has a 1 in it somewhere. Which trig function do you flip to get cosecant? You flip the sine. Okay, now treat this just like you would if it were numbers. Multiply by the reciprocal. So keep the top the same. And multiply by the reciprocal of the denominator. So the reciprocal is sine over 1. What do I get for a final answer? James?
Cosine.
Just cosine. So if you take the cotangent of any angle and divide by the cosecant of the same angle, it's going to be the same as just taking the cosine. So in calculus, you'll do this a lot. You'll take expressions that look complex, make them easier to work with. So the homework, it's a couple questions of each of the different types we did. So a little bit of unit circle, actually a lot of unit circle, and then just a couple on identities. So it's 335, 13 to 17, 21 to 25, 29 to 32, 37 through 40, 45 to 47, 50, 55, 56. And I want you to try this one identity. Secant squared divided by tangent squared. Okay, so we'll go over that before our test tomorrow. And anything else we need to go over from the week, we can look at that as well.